Hello, this is Kevin Trainer, and I'd like to welcome you to my lecture on Chapter 10 of the Murach MySQL book, second edition. Chapter 10 is entitled How to Design a Database. I'm going to leave you to read over the objectives on your own. And this brings us to our first slide about database design. So, relational database design is it's a pretty well understood activity. I mean, we've had relational databases since, well, they were invented in the late 60s, and they kind of came of age in the 70s, and they became widely used in the 1980s. So they've been widely used for over 30 years. So a long time. And people have been designing them for a long time. And the people who sort of invented relational databases were very thoughtful people. And there are several groups of thoughtful people that surrounded the technology. So there's been a lot of good thinking and there's a lot of good practice. Generally speaking, what people do is that they do relational database design in 3 steps. Okay, they do conceptual data modeling. So they'll come up with a conceptual data model, and then they'll review that with people, and they'll make sure that they understand the problem. They've got the concepts down, and then they'll go in and then they'll make it more relational database like. They'll create a logical data model, and then they'll work out all the details of that, and then the last thing that they do is that they'll just add the physical details. So they do physical data modeling. Okay, so when you look at this, when you look at the slide here, it looks like a one-step process. Okay, and it's really a 3-step process, but we're kind of shortening it here. So we have a real-world system. Okay, we have things in the real world that we want to be able to track. A lot of times people call these entities, right? And eventually we want to go from just a list of things in the world and in our system that are interesting to a design for a database. And of course, as we know already, the design for the database is going to be in terms of tables, and those tables are going to work in terms of rows and columns. So Joel Murach has identified 6 steps that go into designing a data structure. 1 is to identify the data elements. 2, to subdivide each of the elements into its smallest, most useful components. 3, identify the tables and assign the columns. 4, identify the primary and foreign keys. 5, review whether the data structure is normalized. And 6, identify indexes. And this is really, I think, slanted towards the final step of data modeling, the physical design. Okay? So I just want to point that out because I'll try to backtrack a couple of times before we go through to the end. So one of the things that we need to do is we just have to kind of understand the data that's in our system's environment that we're trying to create. And one of the ways that we can do this is just to look at documents. We just look at the documents that surround us, Typically, there's an existing system or there's a existing kind of manual process, and whatever's out there should be throwing off lots of documents, things like this invoice. And we can look at them and we can come to understand what a lot of the data in the system should look like and what some of the relationships are amongst the elements. So we can look at forms and reports and such in order to identify the data elements of interest. And so here's what we've done is we've made up a list from that invoice document. Here are all the data elements that we found on the document. So the vendor name, the vendor address, the vendor phone, the vendor fax, invoice number, invoice date, a lot of stuff there, okay? And when we're trying to think of the candidates for data elements that we're going to want to use, okay, these are things that are going to, we're going to be deciding what columns are going to be in the database, right? One of the things is to make sure that we divide the data up into its constituent parts, because I think as we saw in the last of the chapters, with names in particular, it's very hard to if in fact we've got columns for excuse me, first name, middle initial, last name, okay, we can always concatenate 3 columns and come up with 1 column in our result set that is a properly expressed full name. But if we store 1 column as the full name, it's worth your life to pull it apart again. And we saw a couple of expressions for that in the last of the chapters, and they worked fairly well, but they're not foolproof. So what we generally want to do is we don't want to store things in a pre-processed kind of way. So here's the case on slide 8 where we've got a vendor sales contact name, and the vendor contact name is Ruben Goldberg, and we've decided we're going to store it as a first name and a last name. And this is typically what we would want to do. We don't want things aggregated when we are designing the database. We want them disaggregated, and then we will re-aggregate them when we need to. The same thing with the address. In a typical address, we don't put the address all into 1 column. We typically have 1 for street and number, 1 for city, 1 for state, 1 for zip. Okay? Now, this gives us the opportunity to format the vendor address in a number of different ways when we're doing our queries. And if we want it combined, well, we can simply concatenate the columns in a way that would reproduce that vendor address all as 1 string. Okay, so possible tables and columns for an accounts payable system. Again, the accounts payable database is what we use for a lot of our examples here. And let's see, we've got vendors, vendor name, address, city, state, zip code, phone number. We decided that we're not interested in some of these. We've got vendor contact first name, vendor contact last name. And then we've got invoices, invoice number, invoice date, terms, payment date, payment total, invoice due date, credit total, account number. So these things over on the right side, these things with the asterisk, kind of relate to possible other tables. The terms, maybe the terms should be detailed in a terms table. The invoice number, um, uh, that wouldn't come from another table, but the account number, that's probably going to come from a customer table. We've got some more stuff here for the vendors. We have terms and account number. We've got on the invoice, invoice number, account number, sequence number, a bunch of different stuff here. So here's the notation that Joel likes to use. It's a little bit different than mine, and I apologize for not being as familiar with it as Joel would like me to be, and probably you would too. Data elements that were previously identified but aren't needed are crossed out. Data elements that were added are displayed in italics. Data elements that are related to two or more entities are followed by an asterisk. Okay? And these entities are things in the world that interest us. So when you do a full-blown relational database modeling methodological approach, the first thing that you do is a conceptual data model where you are identifying the entities involved and their relationships. And we'll be showing that. We've shown entity relationship diagrams previously in the course, and we'll be going through them at the end of the chapter again. Okay. But it's important to remember that entities are things in the universe that we are interested in. They are things like invoice. They are things like customer. They are things like product, right? So having a good idea of what those things are is going to help us in our design. So here is kind of the beginning of an entity relationship diagram. It doesn't use the notation from any particular diagrammer, but it's close enough that you should be able to get the idea. Okay, so we have entities, vendors, invoices, invoice line items. Okay, so these are the things in the world of our problem set that we are interested in. And then we have the relationships between the entities. And all we can really tell right here is that between vendors and invoices, there's a one-to-many relationship. So for a particular vendor ID, there might be 0 to many invoices. And then when we go over to invoices and we look at invoice line items, for a particular invoice ID, there are probably 1 to many invoice line items because we're not going to have an invoice that doesn't have any line items on it. Okay. So not quite the notation that I've showed you before, but you get the idea. Okay. Here's our two tables with a many-to-many relationship. Okay. Now, one of the things that is interesting is that in entity relationship diagrams, you can create a many-to-many relationship if you're creating a conceptual data model. Unfortunately, relational databases don't implement many-to-many relationships directly. So here is an example that The relationship between employees and committees is many to many. And the only way to make this work in a relational database design is to have a table in between. Now, Joel calls this a linking table, okay? In conceptual data modeling or data modeling, entity relationship diagrams, we call this an associative entity, okay? Some people would call this an associative table, but it's a table that resolves the many-to-many relationship between employees and committees. And how do we do that? Well, it's pretty interesting. The the primary key of the employees table is employee ID. The primary key of the committees table is committee ID. How do we link them together? Well, we have a memberships table. Sometimes if you can't come up with a name for it, you just combine the two names. You call it employees underscore committees. And what's in that table? Well, each row has the employee ID and the committee ID, so it links the two. So the combination of those two columns, employee ID and committee ID, make up the primary key of memberships. And each half of that is a foreign key that points across to the table that it links. So from memberships, the employee ID points at the employee. From memberships, the committee ID points at the committee. And these linking tables sometimes have intersection data. Oh, they might have something like the date that somebody joined the committee. Okay? Or if all you're trying to do is to say there's a relationship between this employee and this committee, and they all have the same relationship, they're members of the committee, well then it's all key. Linking tables can be all key. And that's what we have here. Here's two tables with the one-to-one relationship. So we have two tables here, and I'm going to repeat a distinction that I've made, I think, several times during the course. There are people who design relational database in which they give plural names to the names of the tables. So Joel Murach is one of these people. So he says it's the employees table and the employee photos table. And then there are people like me who are more kind of old school, hardcore, who learn how to design these things using entity relationship diagrams. And in entity relationship diagrams, when you're doing conceptual data modeling and logical data modeling, it's considered correct for the names to be singular. So it would be the employee entity and the employee photo entity. So you're going to have to decide who you want to follow on this in terms of when you finally get to create your own tables. But if you follow me, your tables would be called employee and employee photo. And if you follow Murach, and there are some people who do, I just happen to think they're wrong, you'll say employees and employee photos. But here's a one-to-one, okay? Now, it's kind of interesting. One-to-one table relationships are kind of suspicious, okay? Here's why. Well, we have the entity employee, okay? And let's say that each employee has a photo, okay? Well, let's say they always have a photo. Okay. So that means that we're always going to populate that. Well, why not simply make that an attribute on the employee entity, or when we talk about tables, why not make that a column on the employee's table? Well, there's a couple of reasons that you might not want to. One is that the photos might be really big. They might take up lots of data. Okay, and it turns out that in order to manage the space in your database, you would want the photos in their own table. Okay, well, that's an argument for it, I guess. The other is it isn't really a one-to-one relationship. It's a 1 to 0 to 1 relationship because the employee photos are optional. Not everybody has one. So as soon as you get optional things, I think you can have these 1 to 0 to 1 relationships where we don't want to take up the space for a photo unless we really have a photo. It's an optional photo. Okay? So apart from that, if it's not optional information, if it's required and there's one and always one, then I think we would want to keep it back in employees. Now, when we set up the relationships between the tables, we do these things with typically we have a foreign key on one table which points across to the primary key on the other table. And which side points to the other side? Well, if it's a one-to-many kind of relationship, which we have a lot of, we always point from the many side to the one side. So the table that can have the many, it's the one that has the foreign key column. It typically has the same name as the primary key column in the other table, and it points to it. Okay? If it's a one-to-one kind of a relationship, well then we have to pick one. But we typically don't point both ways. Okay? We typically don't have things pointing, we don't have two tables where they each point back at each other. We typically have one that points at the other, and then we have this index, this index for the secondary index field that allows us to query the relationship going in either direction. Okay? So these relationships that are created with foreign keys, when we write the code that implements the database, when we define the table, we will set up a constraint that says that we will not break referential integrity. So let's talk about what that means. So deleting a row from the primary key table. If the foreign key table contains one or more rows related to the deleted row, okay, we can't go and delete the row in the primary table that secondary table is pointing to. You can't pull the rug out from under it, okay? So how could you do that? Well, you could go to the table that's doing the pointing, okay, on the many side of the relationship, and you could either delete those rows, sometimes we do, or you could change the row that they're pointing to in the primary key table, okay? But so long as you have rows pointing to a row in the primary key table, you can't delete that row from the primary key table because of it would break referential integrity and it would violate a foreign key constraint. Likewise, inserting a row in a foreign key table. Okay? If the foreign key value doesn't have a matching primary key in the related table, then you can't insert the row. And we've seen this before, but we just want to emphasize it here. If if I have a customer uh, and well, on a sales side, I have customer and invoice. So each invoice is for a customer, right? Well, when I go to insert the invoice, um, I go to populate that foreign key, it has to point to a customer who's really in the customer table, or else it will violate the foreign key constraint and the insert will fail. Also, when updating the value of a foreign key, if the new foreign key value doesn't point to a real row in the primary key table, well, then that won't work either. And updating the value of the primary key, if the foreign key table contains one or more rows related to that row that's changed. So we're really only talking about the primary key value, okay? You can change column data on the primary table that we're pointing to. That's fine. You just can't muck with the primary key. Okay, and generally speaking, the idea that you want to change a primary key value is a little ugly. Okay, primary key values are so important to the identity of things in our system that I think we do well to think of primary keys as being permanent, and that if we wanted to change a primary key, we could delete a row and then add a row back with the right primary key. Terms to know: entity, a thing in our problem space that we want to track. An attribute. An attribute is a data item that relates to that entity. So on entity relationship diagrams, we have entities that have attributes. When we convert those into relational tables, we have tables that correspond to the entities, and we have columns that correspond to the attributes. Instance. Okay, so we have an instance of an entity that it would be a row that occurs in a table. Okay, so if we have the customer table, each instance of customer takes up a row in the customer table. Entity relationship modeling is a diagramming approach that helps us get a handle on what the entities are in our problem space and what their attributes are and what their relationships are in preparation for coming up with a design of relational tables. Referential integrity is the requirement that when we have foreign keys that relate one table to the other table, that we have to maintain the relationship rules when we are inserting, deleting, and changing values such that the relationships are not destroyed. Declarative referential integrity is a feature of relational databases where we can declare what the relationships are, and we can tell the product that we want to maintain the referential integrity. So we can do that with MySQL. We do that with a foreign key constraint when we're defining the table. And an orphaned row is what we don't want to have. That's what could happen if we didn't maintain relational referential integrity with foreign key constraints. If we had a row in a table that had a foreign key that pointed to a primary key table, and then we deleted that row in the primary key table, that the row in the foreign key table would be orphaned because we would have broken referential integrity. Because we have foreign key constraints that implement the relationships in our database, that's not a possibility for us. Okay, normalization. All right. We gave some hints to this in a couple of chapters ago. Okay, so there's a difference between relational tables that have that have a design, and relational tables that have a good design. All right, there's a goodness kind of aspect of it. And generally speaking, well-designed relational tables are normalized. And normalization is a way of getting rid of, it's really doing two things. It's getting rid of approaches that are just not relational table approaches. Okay, it's not the way we do it here. Okay, or getting rid of potential redundant information. So this is the first thing, is not the way we do it here in relational databases. Okay, so here is we have a table where we have a vendor name, we have an invoice number, then we have item description 1, item description 2, item description 3. So we've got more than one column that serve the same thing. Okay, we call these repeating columns. Okay, we don't want repeating columns. Okay, why? Because it's not the way we do it in relational databases. If we have repeating columns, then our solution for that is to break it out into a separate table. We'll show you how to do that. The second example on slide 18 is an example of redundant data. Okay, so here we have vendor name, invoice number, item description, and we've got, I guess, the repeating data here is the vendor name. Okay, so if this were a table, we of course would not save the vendor name, we would save the vendor ID, and we would have a relationship to a vendor table that would have a vendor ID and the vendor name. By recording the vendor name on each row of an invoices table, we have the problem that we have it expressed redundantly. Okay, and that's just not how we do it with relational databases. One change, if Kaner's publishing were to be acquired by ABC Inc., well, then we'd have to go and change that in a lot of rows. If we had squeezed the redundancy out of it and we had a properly normalized database, then that name Kaner's Publishing would be in a vendor table. There'd only be one row that said Kaner's Publishing, and we would go and change that to ABC Inc., and that would change it in our whole system. Okay, so repeating columns, not the way we do it. Storing redundant information, not the way we do it. They both break the rules of normalization. Okay. Now, so there are several normal forms. There are first normal form, second normal form, third normal form, and there are normal forms greater than third normal form. They just keep going up. Okay? Uh, there are courses in which we try to teach you which normal form is which rule. Okay, so for instance, the repeating columns, first normal form. So if you keep repeating columns, you've broken first normal form. Okay, now beyond that, it gets kind of hazy when you read the definitions. What normal form have you broken? I believe that it doesn't matter which normal form you broke. If you have redundant information, you've broken normalization rules. Okay? So when we take all the stuff that we have here in the accounts payable system, we come up with vendors is one table, invoice is another, invoice line items another. We've got terms, which has a relationship to invoices and vendors, because each vendor has a default terms ID and in each invoice has a terms ID. And then we have general ledger accounts, which each invoice line item is for a general ledger account, and each vendor has a default account because there are times when we buy, if in fact we buy the same things from the same vendors on the same terms, they put these two defaults on the bottom of vendors as a way to do kind of quick data entry. So I'm assuming that the way this system's going to work is that when we go to put in a new payables invoice, that the field for terms is going to default to the default terms, and the account number is going to default to the default account number. And if they're not the right ones, then we're going to go choose the right ones. Okay? So this is normalized. So terms to know: normalization, redundancy. We don't want redundancy, which means that we want columns to appear only one time in the database unless they're appearing as a foreign key. Okay? In which case they simply point to the table that has all the data. Right? An unnormalized data structure is one that hasn't been normalized. A normalized data structure has had the redundancy squeezed out of it. Normal forms, there are several: first, second, third, fourth. There are other kinds of normal forms. In general, they all have to do about getting the columns on the proper table in order to eliminate redundancy. Indexes. Okay. Now, the physical databases need indexes so that the row that you're looking for can be found quickly when your query is being processed. Okay? So, what do we create these indexes on? Well, when a column is frequently used in search conditions or joins, we might create an index for it. When a column contains a large number of distinct values, we might create an index for it. When a column is updated infrequently, we might create an index for it. We always create an index on the primary key. Okay? So when we're trying to find things by primary key, the server doesn't have to go and scan the entire table in order to find the rows that we want or the row that we want, because the primary key is going to be unique, right? In MySQL, we automatically create an index on every foreign key column. So between the primary key index on the primary key table and the foreign key index on the foreign key table, the server can navigate across a relationship just as fast in either direction. And it's because we have those two indexes that we only have to point one way in a relationship. So we only have the foreign key on one side. In a one-to-many, we have the foreign key on the many side. It points back to the one side. When we go to traverse it in the other direction, we can use the index that's been created for the foreign key, which is done automatically in MySQL. Okay, some normal forms. First normal form. The value stored at the intersection of each row and column must be a scalar value, one value, not a series of values. And a table must not contain any repeating columns. Okay, so we can't have a column that we define as containing multiple values, or we can't have repeating columns. First normal form. Every non-key column, this is a second normal form, every non-key column must depend on the entire primary key. This really comes down to having placed the column on the right table. You break this when you've put the column on the right table, either because this is the only place where that column appears and you put it in the wrong one. It really goes with another table, another entity. Or because you've got duplicate columns. You've decided that you're going to keep the customer name in the customer table and in the invoices table. No, you don't do that, okay? You're going to keep the customer name in the customers table, and the only customer thing that's going to be in the invoices table is customer ID. And then third normal form, every non-key column must depend only on the primary key. Again, this is a fancy way that says you put the column in the wrong table. Okay? So if you have columns that appear in more than one table, and they're not foreign keys that are pointing to the other table, then you definitely have some kind of normalization problem. Okay, unless it's a common name like name, right? It has a different meaning in different tables, but customer name ought to appear in one table. If you've got customer name in more than one table, you have a normalization problem. Okay? There are all these other normal forms. We usually start after third normal form, but there's Boyce Codd, fourth normal form, fifth normal form, domain key normal form, sixth normal form. We're going to be satisfied with third normal form, which is essentially no repeating groups, no multiple values in one column, all of the columns on the proper table, not the wrong table, no duplicate columns, except for foreign keys that point to the data on the other table. Okay? The benefits of normalization. You have more tables, and each table has an index on its primary key. that makes data retrieval more efficient. Okay, so well-normalized databases are more broken down. They're more kind of atomic. We don't have things combined. That's especially helpful when we go to look up things kind of individually. If we want to find a customer name, we just have to look through the customer data. If we want to find a product name, we just have to look through the product data. Instead of having them combined in, say, the invoices table where we'd have a lot of redundant information and we'd have to factor things out. So there's a basic retrieval efficiency to this kind of approach. Each table contains information about a single entity that makes data retrieval and insert, update, and delete operations more efficient. Okay? They're less likely to be mistaken, too. Each table has fewer indexes, which makes insert, update, and delete operations more efficient. Now, we haven't said this explicitly yet, but these indexes have to be updated when the data changes, if we do some kind of update. Now, the primary key indexes are pretty good because we don't change primary keys. Okay, so we're not going to be updating a primary key. But every time we insert a new row, we have to go insert another row in the index. Okay, so we don't want a lot of complicated indexes. Okay. Data redundancy is minimized, which simplifies maintenance and reduces storage. Now, this is what normalized relational databases are all about. And here I'm just going to say that this normalization approach is the gold standard for online transaction processing databases. What kind of databases are these? Well, this is the database that you have to support your payroll system, your HR system, your manufacturing system. These are the databases that record the data and the records of the everyday transactions of your business. Okay? We originally wanted to get rid of the redundancy because we wanted to save storage. Storage is less expensive, disk space. Okay, storage is less expensive than it's ever been, so that's not as big of an issue as it was. The problem in having redundant information in these online transaction processing databases is as soon as you can have the data in more than one place, then which is the correct one? Okay? If you have two things, if they agree, that's great. But if they have the potential to disagree, then you're gonna, as soon as they disagree, you've lost confidence in that database. Okay? So one of the reasons for not keeping redundant information is that we don't want the potential for degrading the reliability, the trustability of the data. Do we normalize all databases? Not anymore. Well, what kind of databases are there other than online transaction processing databases? We have databases that are used for data analytics, okay? Big time data analytics. So these would be, say, big data applications. They would be data mining application. They'd be text mining applications. They would be applications that would be using a large corpus of text, trying to analyze it, or they be using a lot of numerical data, trying to mine some facts out of it. Um, the problem for those applications in using normalized relational databases is that um, they are compute bound. Okay? So for normal online transaction processing databases, we're more concerned about the threat of redundant data and the size of storage. Um, so we go to normalization. As soon as we get to things that are compute bound in a way that online transaction processing is not, we are willing to relax the normalization standards. So the databases that people design for things like data warehouses are denormalized. Okay, so there is a particular approach to there are a couple of approaches to designing databases for data warehouses. One is called a star schema, and it's a highly denormalized approach. Um, why are we not? Why do we do it? Well, because we want to make things more computationally feasible. We want to get the answers sooner, going through lots of data. Why are we not concerned about redundant data? We create data warehouses, and most of the data that we analyze this way is extracted from online transaction processing systems. So we extract the data from online transaction processing systems, and we build a data warehouse that's denormalized. Okay? We typically don't maintain changes in the data warehouse. What we do is we go back and we rebuild it. So we rebuild it once a year, we rebuild it once a month, once a week, once a quarter, once an hour. Whatever we do, we rebuild the data. So we don't have to worry about getting things out of sync with each other, because what are we extracting the data from in order to build this data warehouse? Well, we're extracting it from normalized online transaction processing databases. So when we have these kind of output only applications like data analytics, we're willing for the underlying data in the data warehouse to be denormalized. And that's a whole different course. That's a whole different thing to do. For what we're learning here, are these online transaction processing databases, we want the data to be normalized. Okay, so let's look at some, we're back to we want things to be normalized. Okay, so let's look at unnormalized invoice data here. So here's invoice data with a column that contains repeating values. Okay, so if you look at item descriptions, we've got repeating values. Okay, then we have invoice data with repeating columns, which would seem a little bit better, but it's not. It's kind of the same deal. Well, how would we solve that? Well, we would put it to first normal form. So we have the vendor name, the invoice number, the item description. Now, I just want to point out here that this is not the vendor name. Okay? I mean, it's the vendor ID. Right? So we would have but we would not. The point that we're trying to make is, if in fact we have 3 items on invoice number 112897, we'll have 3 rows in the table. Would we keep the vendor name in that table? No, we wouldn't. Okay. Why he's got this column here is kind of beyond my mind. Okay, so forget about it. Invoice data in first normal form with keys added. Okay, so he's getting better. He's got invoice ID, invoice number. Invoice ID, invoice number, invoice sequence, item description. And now he goes to second normal form, invoice ID, invoice sequence, item description. Okay, so this is normalized. Okay, these other things were just this typical, well, we'll try this, and okay, that didn't really work as well as we'd like it to work. So the invoice accounts payable system in second normal form. So here are the invoices, here are the invoice lines. So he's got invoice ID, invoice sequence, account number, line item description, line item quantity, line item unit price, line item amount. Okay, so that's certainly better than what we had seen in a denormalized version of same. Questions about the structure. Does the vendor information depend only on the invoice ID column? No, it doesn't. The vendor name, the vendor address, it depends on the vendor ID, at least in the way that they talk about this. Does the terms column depend only on the invoice ID column? No. I mean, we could share terms. Perhaps the terms ID does. Does the account number column depend only on the invoice ID column? Not only on the invoice ID column. No. Can the invoice due date and line item columns be derived from other data? Yeah, they can, because we have information about the whole invoice that we're keeping on the invoices table. So now we've come to third normal form. Okay. So we've got vendors, invoices, invoice line items, general ledger accounts, and terms. Okay, so things that are the only so for instance, in the invoice line items, we're not keeping the account description, we're only keeping the account number. Okay, and in the in invoices, we're not keeping the terms description or the terms due days, we're just keeping the terms ID. Okay? If we were to keep more than that, it would be redundant data. This is normalization gone too far. Okay? What do I mean by that? Well, this is the form of normalization that most people don't do. Okay? So, for instance, most people keep the actual zip code in the in the vendor table. They don't have a table of zip codes and put the zip code ID there. Okay? Same for area codes. All right? Could you do that? You could. Is there some potential data quality improvement? Yeah, you probably could. Like, for instance, you couldn't get any non-valid zip codes or non-valid area codes, so that has some benefits. Do most people go that far? No, they don't. Fifth normal form is farther along than most people go. Okay? Line item description ID, okay? Sometimes some people might say, well, we want to control values in the line item description, so we'll have a table for that. So it's a question of how much you want to control values. Okay. This, for most people, is too far. All right. When to denormalize. Well, I talked about this already. When a column from a joined table is used repeatedly in search criteria. So if we, there are times when you come up with a completely normalized design and it's just not running fast enough. Okay, so people will back off and denormalize it in order to speed it up. If a table is updated infrequently, again, to speed it up. To include the columns with derived values when those values are used frequently in search conditions, again, to speed it up. So generally speaking, people completely normalize the database to third normal form. Okay. And then they only back off and denormalize it if they have a performance issue. So here we're showing MySQL Workbench. And we're going to introduce you to the capability of creating ER diagrams, or in this case, EER diagrams, extended entity relationship of model diagrams, with this capability. Okay? So you can create an EER model with the graphical user interface. Okay. Another thing that you can do is you can reverse engineer. So you can take an SQL creation script for creating a database, and you can take that and you can say, I want you to create an EER model for that database. Instead of creating the database, create an EER model. Okay. Here's an EER model for the AP database. Okay. So we're looking at the vendors table. Operations for working with an EER model. You can edit a table, you can add a new table, you can delete a table, you can display a diagram, you can create a new diagram, you can create a database creation script from the model. Here's an EER diagram for the AP database. Okay. Did we recreate that from scratch? No. We took the script for creating the AP database and we used it to create the EER diagram. I think I went the wrong way. Oh, wrong. Here are the operations for working with an EER diagram. Add an existing table to the diagram, add a new table to the diagram, display the model for a table, define the relationship between two tables, edit and delete relationships, remove a table from the diagram, and optionally from the model. So I'm going to put together a demo, a tutorial demo, where I go through how to use a diagrammer and a little bit about the database design concepts that I want you to be thinking about. All right. So I'm going to say bye until then. So bye-bye.